Hello, y'all. Barely Berry Jr. back with some more physics. We'll go back to our reading as we were doing earlier. So I had started the. Hold up, let's try to get everything back. I forgot I changed things around. Try to make it fit better. There we go. So we're going back to what I did before, where we were looking at the matrix and linear algebra formulations for these matrices that form the Euler angles that represent a transformation of a rigid body around a fixed point. We saw how these um, formulations were very similar to the linear algebra formulation for a coupled oscillator. So the last video I did a coupled oscillator in detail, and we was able to see the linear algebra formulation. So what I'll do here is continue from where I left off with this 4.58. And we know that when we're doing these problems with rigid body in 3D around a fixed point, we know at least one lambda is going to be 1 because that's going to be the column and row where the rotation happens. All right? So comparing equation 4.58 with the secular equation 4.52, or they call it a secular equation. The same thing, except there's no lambda. You see that one of the eigenvalues satisfying equation 4.52 must always be lambda equals 1, which is the desired result of Euler's theorem. Note how the proof of Euler's theorem emphasizes the importance of the number of dimensions in the space considered. In spaces with an even number of dimensions, equation 4.57, is an identity for all matrices, and Euler's theorem doesn't hold. Thus, for 2 dimensions, there is no vector in the space that is left unaltered by rotation. Okay. The axis of rotation is perpendicular to the plane and therefore out of the space. Okay. It is now a simple matter to determine the properties of the other eigenvalues in 3 dimensions. Designate the +1 eigenvalue as lambda 3. The determinant of any matrix is unaffected by a similarity transformation. Hence, by equations 4.54 and 55, properties of A as a proper rotation transformation matrix is lambda, lambda, lambda. We're letting lambda 3 equal plus 1 and equals 3 for 3D space. And this is 4.59. Further, since A is a row matrix, then if lambda is a solution of the second equation 4.52, looks like that was the word I was looking for in the last video, secondary equation. I called it, what I called it. And the solution to the second equation, the complex conjugate must also be a solution. If a given eigenvalue lambda I is complex, then the corresponding eigenvector Ri that satisfies equation 4.59 will in general also be complex. You can have complex lambdas. We have not previously dealt with the properties of complex vectors under real orthogonal transformations, and there are some modifications to previous definitions. The square of the length or magnitude of a complex vector R is R dot R complex conjugate. So we have the two lines for the magnitudes, that's using one for the determinant equals and the stars for the complex conjugate. For orthogonal transformation, the square of the magnitude is invariant. Let me check this equation really fast. Each one individually. no number. The square of the magnitude is invariant. Suppose now that R is a complex eigenvector corresponding to a complex eigenvalue lambda. Hence, by equation 4.49, we have hey, what's going on, Ben? Let me know what questions do you have, and I can clarify. Thanks for dropping the line, by the way. I don't know what is clear or unclear if when the writer lets me know what sticks out. Okay, so what these are vectors or matrices. So going back to, matter of fact, I just copied it here. So let's say that we have a matrix, which would be something like this: A11, A12, A21, A22, for example. And then you have a vector X, or I'll just say R1, R2. And this simply refers to these vectors and matrices, and also to the complex conjugate of the same. So the complex conjugate would be if you take the vector and any imaginary part of it, you put a negative on it. So let's say R1 equals A plus IB. Then R1 complex conjugate would be A minus IB. And let's say R2 is C plus ID. So R2 complex conjugate would be C minus ID. So R star would, in this example, or be R1 equals A minus IB, and R2 equals C minus ID. So this is just a vector, or in this case, a vector. Suppose it could be a matrix as well. So an aura swiggle on the top is the transpose, which means I take all of the rows and make them columns, and I make all the columns and make them rows. So this would be A11, A21, and A12, A22. So you can see here I just turned it sideways, and that's taking the transpose of that matrix, which means that when you see this term RAAR, now of course these are not the vectors and matrices we're working with, but this is what it would pretty much look like. So R would be, for example, this, and A would be another matrix here, turned to the side. Well, I probably should have put my R's there, but hopefully you see what I'm saying. Anyway, this will be, I'm mixed up in, this would be R's. These will go there. I would have a different matrix for A right here. And so the A would be this. The R complex conjugate would be this, but you are plugging these complex conjugate R's. The A transpose would be this with the role swap like I showed here. And that's all that is. So it's just when you're learning the concepts, I usually just speak in generalities where instead of putting in the actual matrices, and of course, this is actually continuation from previous videos in concepts. So like for instance here, I might have deleted a line right there. But in this case, when we think of A, because really we're working in 3D, you could always think of that. And aura, in this case, is the vector x, y, and z because we're dealing with 3D. And the complex conjugate of A would be, instead of this first row going down like this, that'll end up being like this. And this one will turn around sideways, so it's like this. And that'll be the transpose one. And the complex conjugate, again, would be just putting the negative on the imaginary part. You're certainly welcome. Let me know if any other questions come up. And some things it'll be just I need to explain better. Some things it'll be because it's a continuation. So, but I'm happy to reiterate. A new person joins, just let me know, hey, that's not clear, and I'll be happy to reiterate where it comes from. So we have this. So now what they're saying is, for the next line, I kind of hate when they don't put numbers on the equations, but we have aura transpose, so we know that we swap the rows and columns, make the vertical rows horizontal. We have aura prime complex conjugate, so we know we change the sign of the imaginary part, and that equals, so we have our lambda here. So we have the first lambda, we have the complex conjugate lambda, and then we have the R swiggle and the R complex conjugate. And this is just because looking at the correlation, we have R prime on this side, we have R and no prime with lambdas on this side. So this is just twice the same thing multiplied by each other, with one of them, one side, both sides actually being a transpose and complex conjugate. All right. It is easier to do this stuff when you deal with an actual example, but I am starting to appreciate going through the process first without numbers as well, which leads to the conclusion that all eigenvalues have unit magnitude. Okay. I'm not sure. It seems that they're talking about the fact that we have this, because one of them is going to be 1. All of them multiplied still has to equal 1. Some of the details still escape me as well, but we're going through it. So lambda complex conjugate equals 1, and this is 4.60. From these properties, it may be concluded that there are 3 possible distributions of eigenvalues. If all the eigenvalues are real, then only 2 situations are possible. Okay? So 3 situations. Let's see if I can put this in a table. So we have eigenvalues are real. Eigenvalues are, is it complex or imaginary? I'll put complex. I mean, they pretty much mean the same thing, but I'm not sure what's the best one to put. And so we have 2 situations for real, 1 for complex conjugate. All eigenvalues are +1. Lambda I equals +1. The transformation matrix then is just 1. A equals, this is the identity matrix. One eigenvalue is 1. Lambda, I'll call this lambda 3 equals 1. And the other two are both -1. Lambda I equals -1. So we only have two other ones. I is from 1 to 2. Such a transformation may be characterized as an inversion in two coordinate axes. So I did that the other day. We looked over that, I believe, with the third unchanged. Equally, it is a rotation through the angle I about the direction of the unchanged axis. So it's talking about if we have a coordinate system like so, and this is x, y, z, and this is my vector, and if one axis remains unchanged, but I transform the other two axes, then it'll be what? This will be the unchanged axis by z. So that's not going to change. So this equals constant. So all we have is this one and third one. That's right, because it's only on one plane. Let's stay stationary. They're unchanged. Interesting. So I guess they simply mean that these two coordinate axes, what I call this x prime and this y prime, those two coordinate axes change. We have theta there and we have theta here, like so. About the direction of the unchanged axes, which you can see they're rotating about the z-axis, if that's clear. So basically z is like coming out the page, basically. So I'll just erase z since we're not moving around z. So now you have x and y in the plane. The vector's out there somewhere. But I don't see the inversion though. Earlier, I did an actual inversion where it came up underneath the plane. That was from all three, right? It's still a little bit unclear. And let me run and get a drink of water. I'll be right back. I have a water bottle with me. Be right back. That is much better. Okay. So we have that one. I'll erase this. So you have one where they're real and one is lambda. Well, all of them are one. All the lambdas are one. You have one where, because again, all of them multiplied together has to equal 1. So remember that they're talking about this fact having to be true, right? here. Then I'm going to highlight the whole thing in yellow. So they basically looking at ways that equation 4.19 is true, where all the lambdas multiply with each other and still equal 1. Either they all can be 1, 1 can be 1, which I call lambda 3 1 like the book does, then lambda 1 and 2 are negative 1, or if not all the eigenvalues are real, there's only one additional possibility, which is one eigenvalue is plus 1. So we'll say lambda 3 equals plus 1. And the other two are complex conjugates of each other of the form and lambda I equals E. What's the best way to write this? I phi. Uh, I guess I should just write these then. Actually, I'll just say plus minus. I'll see if there's any questions. Awesome. Welcome, y'all. Thank y'all for watching. Let me know if y'all have any questions or comments, and I'd be happy to reiterate. So we have this. So, of course, the way this will work is if we have, and I'll just erase this line right here. And as an aside, if you have lambda 1, lambda 2, lambda 3, this will be 1 e to the I phi e to the negative I phi. So this will be e to the I phi minus I phi, which is e to the 0, which equals 1. So that's why that's equal 1 right there. A more complete statement of Euler's theorem thus is that any non-trivial real orthogonal matrix has one and only one eigenvalue of plus 1, because this has to be true. And thanks for the shout out there, Ben. I appreciate you pointing out the views. All right, so looking at that, the direction cosines, and the direction cosines, by the way, are these cosines. How far do we scroll? These here. So basically, we have a body in 3 dimensions, and we rotate that body so that we rotate the axis. If we imagine there's a axis in space, and there's an axis that's attached to the 3-dimensional object. When the object rotates, there's going to be an angular difference between the object that's rotating and the original axes. There'll be 9 different angles if you rotate it not along one axis. So these are the direction cosines of that rotation. So for instance, in between theta 1 and theta 1 prime would be theta for phi 1 1, called it theta there, the angle between those. And we can basically get the new axes from cosine 1 1 of the old axes using the definition of, well, it was a long process. So that was, pretty sure I did that on a previous video. It's a long process to derive that. But this is where we're getting that from. These are the angles that we're talking about, the direction cosines. Direction cosines of the axis of rotation can then be obtained by setting lambda equals 1 in the eigenvalue equation 4.51. All right. So we're getting closer to the example. So I'm going to do an example. If I have enough time before, I'll take a break from the graduate level mechanics and do some calculus at the top of the hour. The multidimensional scientific says, "Hi, Daryl. Am I welcome?" Yes, you're welcome. Just don't call me by my gamer tag. Okay. You can let me know your name. I'll call you by your name. I hope you're well anyway. Are you at Texas University now? It's Catherine. Hope is all good. Uh, so right now, everybody, I graduated from UT. So I have a bachelor's in astronomy and a bachelor's in uh, physics from UT. And right now, I'm a graduate student at SMU, Southern Methodist University, which is about 3 hours from UT. So I'm enjoying it here. It's pretty cool. You'll probably see my um, you know, SMU shirts on. Sometimes I'm real big about buying sporting my gear because it's easier to wear. Yes, right now I'm a grad student at SMU, do my TA and stuff, so it's pretty cool. So this is actually the textbook that we're using for my graduate classical mechanics class, classical mechanics by Goldstein and all. So it's pretty deep stuff. So I'm pretty sure this is going to go to. One reason why I like it is because I'm an astronomer by heart. I got a degree in physics and a degree in astronomy. But I picked my graduate schools based upon the astronomy stuff that they're doing. So my main interest is stars. Maybe I can show you all this really fast. So this is a picture I took of the sun right there. So I do some star research here, starting to model stars. I plan on making a video about that, but I think I need to do a bit more progress. I'm still working on it, but I'm modeling stars, and it's fun, enjoyable stuff. I like stars. Eventually, we'll resolve the Hubble tension. I'm working with Dr. Keel, even though we don't pick an official advisor till our third year. But right now, he's pretty much unofficially my advisor. But that's a bit on that. So we have, where were we? The direction cosines of action can be obtained by setting lambda equals 1 in the eigenvalue equation. So here, this is the eigenvalue equation. And thanks for the props, Ben. I appreciate it. And we have this, this, this that we set to 1 and solving for x, y, and z. So it can't mean all of them, I don't think. It says in the eigenvalue equations, direction cosines. Okay. I'll be glad when we get to an example. Oh, yes, I do recall. Right? The angular rotation can likewise be obtained without difficulty. By means of some similarity transformation, it is always possible to transform the matrix A to a system of coordinates where the z-axis lies along the axis of rotation. Okay, so they're going back to this line, or is it this? So this transformation here is the similarity transformation, where, let me copy this whole thing here. I was saying that, oh, sorry. Thanks for letting me know. There we go. Sometimes I forget to switch back when I change screens. So This is what they're talking about from earlier. I just scrolled up and copied this formula down. That's all I did right there. This is the similarity transformation. And they're saying that in this in particular is the similarity transformation, where I have this vector x and I take the inverse of that vector on the left side of the matrix, the vector itself on the right side of the matrix, and it outputs the eigenvalue of the matrix and vector. So this is the eigenvalue, or the proper value. This is the eigenvector, or the proper vector. And this is the matrix A, like we were talking about earlier with Ben. So what they're saying is that this matrix, now keep in mind that this eigenvector, as we talked about in the earlier video, this eigenvalue, I mean to say, is going to be a valid, unique, non-zero answer only when the determinant of this equals 0. Where did I put that? When this determinant, oh, here we go. When this determinant of that equals 0. So I'm pretty sure we're assuming that we got that determinant. We're sure that we have a valid, unique value for the eigenvalue. So now, as long as we have the eigenvector, the inverse of the eigenvector, in the matrix that outputs that eigenvalue, we can output the eigenvalue. But they're also saying that we can get the transformation matrix from setting them all equal to 1, which is new to me. It's so simple. What is the next slide? In such a system of coordinates, A prime represents a rotation about the z-axis through an angle phi, and therefore has the form. So this is becoming familiar to me. I actually derived this last week, if I recall. Yes, matrices are a thing. Yes, they are a doozy, but I'm getting more familiar with them though, especially in this three-dimensional stuff that we have to do now. So every time you go a bit higher up in physics, you realize that the earlier stuff was sort of a simplification of things, and the farther you go, the less simplification you can do. So you have to actually calculate the real stuff as it is, with all the complications and everything. So as the physicists, so what's the word? Aggravatingly say, it gets more interesting. What that means is a whole lot harder. If a physicist ever tells you that part of it's about to get interesting, that's when you know you got to run. Unless you have to stay to get your degree. If you have to stay to get your degree, then stay. But if you can run, just run. This is about to get hard. They're cool. Now, the trace, which is the TR of a matrix, is going to be the multiplication of the diagonal. So the trace, I'll write that, multiplication of diagonal. So that means that the trace of this A matrix that we have there is going to be cosine phi 1, because these are in the diagonal right there, which means we have, and why do they have 1 plus? What up here? See what I'm saying? They're using these trigonometric identities. So you have cosine squared phi. And how did it get? All right. So I have to think back to my calculus class. Like, I know if you're trying to do an integral of cosine squared theta, d theta, that becomes the integral of 1/2 plus, hold up, is it cosine or sine? 1/2 plus cosine 2 theta over 2. I remember right. I think that's right. We need to check on that. I believe this is the identity that they're using. D theta. Nope, they don't have the double angle. Crap. What are you doing there? Am I mistaken? Am I forgetting what a trace is? Maybe it's addition. Is it addition? That was multiplication. It must be addition. It's certainly adding. Crap. Let me look up a trace really fast. And we did cover this in relativity, which I can't say I focused on. I just did what I needed to do to pass the class. But here we go looking at traces again. Is this linear algebra? I believe a trace is linear algebra. Yeah. So it must be addition of the, oh, yep, it's the sum. Damn it. That was the multiplication. Linear algebra, a trace of a square matrix A denoted as TR is the sum of the elements in its main diagonal. Okay, so it's a sum, not the mult. All right, so it's no identity. So add sum. All right, so now it fits and it's not a identity. So we have TR A equals, oh, prime equals cosine phi plus cosine phi plus 1. Now we have 1 plus 2 cosine phi. And then we have, since the trace is always invariant under a similarity transformation, the trace of A with respect to any initial coordinate system must have the same form. Let's redo this again. It's the trace, which is the sum of the diagonal, the main diagonal, is invariant under a similarity transformation. So seems like they're saying if I do a similarity transformation on this matrix, if I have a vector, the inverse of a vector, I sandwich it around the matrix, I get another matrix. Then I take the trace of that, it'll still be 1 plus 2 cosine phi. If I'm understanding that properly, but I may not be. So I'll put TR A equals, and let me check the book to make sure I see the notation there properly. Page 160, check the paper version. So that's I is what that is, and it'll look strange on the screen. Equals 1 plus 2 cosine phi. And I could pause for a second, let me know if anybody have any questions, comments, anything I need to clarify. Oh, and I missed an asterisk, which I rarely do. There's an asterisk on this Z right here. So I'll read this asterisk while any questions or comments come up. If there are multiple roots to the secular equation, which is this, let me copy this down. So say if the secular equation has multiple roots, so if lambda does not all equal 1, and the corresponding eigenvectors cannot be found as simply. It's not easy. Indeed, it is not always possible to completely diagonalize a general matrix if the eigenvalues are not all distinct. These exceptions are of no importance for the present considerations, as Euler's theorem shows that for all non-trivial orthogonal matrices, +1 is a single root, right? So we have to remember that 1 is going to be a part of every single iteration in our experience. This was 4.61. This was an aside. That was the asterisk, which gives the value of phi in terms of the matrix elements. It's interesting. So I imagine it must mean that there's because this book does have some typos. I found that out recently, and my professor confirmed. So maybe they meant to put, because not one psi or phi is going to give different A's. So you have to have a different phi for each A. At least that's what it seems like to me. Because if you have one angle, it's not going to give you multiple answers. So I'm going to assume they mean that this particular phi, 1 plus 2 cosine a particular phi, will give a particular A, I. Remember that the A matrix is this matrix here. So I is 1, 2, or 3. So what it seems to me that they're saying is that 1 plus 2 cosine phi can give each of the elements of this matrix when you get the angle represented by each location, which is, again, if we have wow, these notes are building up. So we have the normal unprimed axes, and you rotate the axes. The angle between theta x1 and x1 prime is theta 1, 1, and so on and so forth. It's like we're just calling them phi right now. But this is what I think they're saying. And Scientific says, I'm wondering about what you're writing on, Daryl, and is it possible to get them with a screen that can look like lined paper? It must be so much easier than carting around huge notepads and folders. Oh, yes, this is an iPad. So, yeah, I swear by them, not any kind of pad. So, yeah, I'll use it. I still have some paper with me because some of our exams are in paper and stuff like that. But all of my assignments and stuff, I do it on a pad. A lot of the professors use pads too. I wonder why they don't all do. The rotation angle phi is to be identified also with the phase angle of complex eigenvalues lambda, okay? As the sum of the eigenvalues is just a trace of A in its diagonal form, okay? Because of course, when we do this, when we all right, when we look at and thankfully I copied that again. When we look at the secular equation, lambda is multiplied by the identity matrix. So lambda ends up being a diagonal, and thus it works beautifully with the trace because everything else is 0. So the eigenvalues is just a trace of A in its diagonal form. Euler's theorem. Oh, now it's starting to make a bit more sense because you're taking the determinant to establish what the eigenvalue is. So remember, the determinant of the secular equation must be 0 for the eigenvalue to be unique, which means that you're taking for the one term in the determinant, you're taking the multiplication of that axis, and each of the terms in the main axis has a lambda. Hence, we have the lambda cubed, which does end up being in the final form of the solving for the eigenvalue, which we may have time to do. One of the viewers earlier had asked about multivariable calculus, so I'll take a break in a little bit and come back and do some multivariable calculus, but I'll probably come back after that video. I'll just take like an hour to do that, then take another break, then come back and finish this. But right now I have a B in this class, and I want to get an A. I think I can. So this is my hardest class, this graduate level classical mechanics. So we'll see how it goes. But I mean, the thing about graduate school is not as important as my understanding. They told me is, I mean, you have to get at least a B to get your PhD, but it's not like you have to get a 4.0 to get your doctorate because everything is hard. So I guess it's kind of rare for somebody to graduate with a 4.0 with a to get their PhD, even though you don't necessarily graduate anyway. You just your first 2 years are classes mostly, and then your after that is research. Even though you do some research initially, like I was saying earlier. But long as you pass your classes to with at least a B to earn your qualification, then you can go for your PhD, and then the PhD is all that matters. So pretty sure they set it for a B because you can miss a few details here and there and get a B. I felt pretty good about my exam. It's based upon one exam that we did. I felt pretty good about the exam, and I got a B on the exam, and I ended up with a B overall in the class given the homework. So I don't think I made too many big mistakes. I don't think on the exam. All right, let's see where we at. Trace in this diagonal form. All right, so let's say 4.54. Right, it is 4.54. Did I miss an equation? No, it's just way back there. Some of these equations are out of order because I copy things, and sometimes I think the book puts equations in not the best order as well. But in this case, it will be good if they was in a better order. The 4.54 is escaping me. Oh, here it is. Oh, it is pointing out the fact that lambda is a vector, which I mentioned earlier. So, okay. I mean, it feels good that they're sort of stating the obvious to me a little bit. I mean, they're getting something of it. By Euler's theorem and the properties of the eigenvalues, the sum is, all right. All right. I know what you mean about wanting to get an A, though. Keep plugging away. We'll try to be here to see you getting there. You'll be fine, I'm sure. Thank you. I appreciate that. Appreciate the well wishes. We'll be back up to 5 viewers. Welcome. Let me know if you have any questions or comments. Thank you for showing up. I'll go for about another 10, 15 minutes on this. I'll take a break. I'll come back and do some multivariable calculus. I'll take a break. Then I'm sure I'll come back and do some more of this because I want to get to where we are in class on this stuff. All right. So I'm gonna write this last thing here. What I'm tempted to do, if I'm remembering this properly, let's actually flesh this out. So we have trace, and this will probably be the last thing I do. Then we'll take a break. Trace of A is going to be the sum. Yeah, 61. Let me make sure I put the proper uh, symbol there. Yep, that's an I. And right? I lambda I equals lambda 1 plus lambda 2 plus lambda 3. So right now they have equals 1 plus E I phi. Where did my pad go? Crap, hold up. There you go. I think I minimized my mistake or something. We have 1 plus EI phi plus E negative I phi. Now, if I was to flesh this out, this would be 1 plus cosine phi plus I sine phi plus cosine phi minus I sine phi. So looking at this expands to that, and this expands to that. So this is Euler's theorem. And we have these canceling, but then we end up with 1 plus 2 cosine phi. Now, one thing I'm not clear about is I guess you can do that because even though the matrix only has cosine along the diagonal, you can add 0. So the original trace is this, which is 1 plus cosine phi plus cosine phi. And you can always add I sine phi and subtract I sine phi because it's really adding nothing to it. And then you can revert that back to this form. So I mean, I could see what that y equals that, but I'm not sure exactly at why they're doing that. We see that the situations in which the eigenvalues are all real are actually special cases of A having complex eigenvalues. Okay. So basically, so a complex number is going to be C equals A plus IB. And if B is 0, then you're just left with the real part. So what they're saying is, or they can be complex conjugates of each other like we just did here. So either they're going to be all real, like we talked about for this rule here. I'll color this so I can get back to it faster next time. Or they're complex, but as we can see, like we spoke about earlier, the complex conjugate is to put a negative on the one of the complex parts. So that means that these are complex conjugates of each other. So you can have one real and two complex with complex conjugates of each other, which is the same thing as saying 1 and or 1 plus 0. All the lambda 1 equals plus 1 corresponds to all the lambda I equals plus 1 corresponds to a rotation angle phi equals 0. Okay, that makes sense. Because if everything has an eigenvalue of 1, then there's no rotation. That's what I'm seeing. While the case of a double eigenvalue, -1, corresponds to phi equals pi as previously noted. So I'm going to have to look at that again. Oh, you know what? I think what I missed on that is the diagonal is going to be the rotations about the same axes. That's what I missed on that rotation thing. No, I did get it actually. I just didn't recognize I did. But I deleted that aside drawing. So I had that drawing where I had one matrix the same, one vector the same, and the other ones were rotating about it. So this is x, this is x prime, this is y prime, this is 1, because it's just rotating, it's not rotating around there. So this does mean that if each of these things is 1, there's no rotation. And if each of these things rotate 90 degrees, then it would be a rotation pi around the axis, like an orthogonal rotation. And welcome everybody who's here. I'll be here for another 5 or 10 minutes now, then I'll take a break, and you can come back for some calculus, multivariable calculus. I'll do a nice basic multivariable calculus equation in 3 dimensions, and we can look at how to get a volume of a shape drawn. Let's see here. The prescriptions for the direction of the rotation axis and for the rotation angle are not unambiguous. Okay? Clearly, if R is an eigenvector, so is negative R, because you could just multiply a constant times it. Hence, the sense of the direction of the rotation axis is not specified. Further, negative phi satisfies equation 4.61. Oh, sometimes I hate them referring to other equations a lot, but I guess it would be too bulky to rewrite all the equations all the time. All right, which one was 4.61? Oh, that one. I wrote that one. Let me highlight it. There it is. 4.61. While the negative side satisfies 4.61 if phi does. Okay. Indeed, it is clear that the eigenvalue solution does not uniquely fix the orthogonal transformation matrix A. From the determinant to secular equation 4.52, which I have there in yellow, and that's the drawing there. It follows that the inverse matrix A negative 1 equals A transpose. Has the same eigenvalues and eigenvectors as A. Okay. However, the ambiguities can at least be ameliorated by assigning phi to A and negative phi to A inverse, and fixing the sense of the axes of rotation by the right-hand screw rule. Uh-oh. We got to the end of this chapter, so this would be a good place to stop. Finally, note should be made of an immediate corollary of Euler's theorem, sometimes called Chasles' theorem. The most general displacement of a rigid body is a translation plus a rotation. Oh my gosh. Oh, Chasles' theorem. The most general displacement of a rigid body is a translation. That means it moves from place to place plus a rotation. And it spins. Detailed proof is hardly necessary. Simply stated, removing the constraint of motion with one fixed point introduces 3 translational degrees of freedom for the origin of the body system of axes. All right. Just we'll read this. Asterisk, then I'll close. It says M. Chasles from 1793 to 1881 also proved the stronger form of the theorem, namely that it is possible to choose the origin of the body set of coordinates so that the translation was in the same direction as the axes of rotation. Okay. Such a combination of translation and rotation is called the screw motion. Okay. And it sounds like they mean right-hand rule. Like if I have a rotation about an axis, normal is up where your thumb is. So if I'm rotating like this and normal is this way and I'm moving that way, it seems like that's what they mean, like a screw motion, because it is like a screw motion. This formalism has some use in crystallographic studies of crystals with a screw axis of symmetry. Such symmetry produces strange optical properties. Aside from that application, there seems to be little present use for this version of Chasles' theorem, nor for the elaborate mathematics of screw motion developed in the 19th century. Well, maybe we'll find a use for it in the future. Awesome. Well, thanks everybody for joining. I appreciate seeing y'all. Thanks everybody for dropping a line in the chat. I'll take a quick break and I'll be back in 20 minutes. I'll actually drop the video. Actually, I can even do that now, making the the video what page that you would see. So it'll be multivariable calculus, and I can do that now. Actually, just need to keep you on while I do that because I have to find the image and everything. But just hang tight, get a snack, come back in 15, 20 minutes. Those who are interested, I'll see you all then. And I'll likely be back later tonight for some more. Actually, I can wait till tomorrow for some more graduate algebra. So I think I'll come back and do the multivariable calculus. I might take a break for the night, and I'll be back tomorrow. So I'll see y'all in about 15 minutes.